Okay, so today we were doing a bit of, like doing a little bit of point set topology to set up for what's to come, right? So a lot of the cool things that we're going to show in complex analysis will come from, will actually be shown via integration, right? So what we'll do is we'll develop complex integration, and after we have that with things like Cauchy's theorem and Cauchy's integral formula, this is going to give rise to us prove, this is what we're going to use to prove most of the really neat results that we'll prove in complex analysis. And we're almost there. So this is sort of all set up until we're able to get there. We're almost there. We need maybe this week more. And we might either even start complex integration next Friday. If not, then the Monday after. Okay, so the Tuesday after, so next week. Okay, so I still have to do a little bit of point set topology. I mean, I can't possibly do all of point set topology. So what I do is I just sort of give some of the definitions and give some some proofs that I think are neat, just to recall the type of arguments that shows up, and we'll skip some others. So if you haven't seen point set topology, you should go and study it a bit. Otherwise, hopefully you enjoy the recalling. And so today we'll go into how point set topology relates with functions. Right, so we'll do that for a bit, and then we'll talk about conformal mapping. So that's the plan for today. Okay, so we define the region, right? Let's say we're some space. I mean, I'm not going to say what is the space we're in, because for now it's not so important which space we're in, but we'll always be later in the complex numbers. But for now, all we're going to say holds for anything. But so let's say, right, we said it's a region, right? You should always think of it as in some kind inside some kind of universe, right? Okay, is a region if it's both, right? This was a definition. If it's open and connected. Okay, and this will be sort of the right place to define functions on, right? Because open is nice, because if you want to understand anything about a function at a point, you can zoom in and there's a ball around that point that's still inside the set, so you can look at limits, you can take derivatives, you can do all sorts of things. And connected is nice because you're going to be able to reason about the function by taking paths from one place to the other, right? If you want things like, well, if I prove that my function has derivative 0, I would like it to be constant, then it better be that the path, the space in which you're defining the function is connected, right? Because otherwise things like this are not necessarily true. And so this will sort of be the natural place to define functions on, okay? So we'll think of functions, let's say, to the complex numbers, for example, right? Define like regions, right? The point is regions are a natural place to define functions on. Okay. Okay, so let's start. Okay, then, we're talking. We had that the function, we defined continuous functions, right? We're going to start relating topology to functions, and we defined the continuous function if it was, if for every epsilon there was a delta, such that if in the domain you were delta closed, then you were epsilon closed in the image, right? But actually, you can define continuous functions for any set, right? So now, I mean, maybe I'll do a theorem, because we're just in metric spaces where we have a distance, and I'll set it up as a theorem instead, right? So f is continuous, right? So remember, all our setup was a metric space, right? In a metric space, right? Where we have a notion of distance so that we can talk about epsilons and deltas, if and only if, right? F, the inverse image of U, is open for all u open. Okay, so a function is continuous if and only if the inverse image of any open set is also open. Okay, okay, so we'll prove this just to see a bit of relations between topology and functions. Right, I'll prove just a couple of theorems of this style. But the point, the point that I want to make already now is that now you can define, right? This allows one to define, right? So with this, now we can define continuous functions without a notion of distance. Right? And while we're not going to talk about topological spaces that don't have a distance, right, that don't have a metric, then in fact you can now define, those are important, and there's a lot of stuff you can show by setting up the right topological space, where you define open sets to be whatever you want them to be. They need to satisfy certain axioms, right? Unions of open sets are open and things like this. And then you're able to actually define continuous functions by basically making use of this, this theorem. Or you can view the other thing as a definition, and it's just telling you that the two definitions we gave are equivalent, as they should be, of course. And so this is actually quite useful, this notion of to be able to talk about continuous functions even when you don't have access to a distance. Okay, but let's prove this, just sort of a warm up for the kind of arguments that go into this. Okay, right, so I have an open set. I want to show that the image is open. So let's do first one. Let's say that f is continuous in the sense of epsilon and delta. Right, so now we want to show that f minus 1u is u, right? So what we have that f is continuous, right? In the sense of, let me write epsilon delta, just so that to remember that, here in the sense of epsilon delta. Okay, this is not part of the proof, it's just sort of for us to remember. Okay, and the goal is to show that if u is open, f minus u is open. Okay? Okay, it's good when we're doing some of these arguments to just write sort of what it is that you have and what it is that you want, and then you can reason about it a lot better. Okay, so let's do it. So let's say I have x. Right, let's take u open. Okay. And now let's take x in the inverse image of u. Okay, but now, right, since u is open, right, it must be that there exists some, okay, let's use some other letter for now. There's used some lambda such that, the ball, right? So f of x, right? U is open, and of course, by definition, f of x is in u, right? Maybe I should. I'll put around the green things when are just sort of things for us to keep in mind, right? So there exists lambda such that b f of x lambda is inside u. Okay, but now, right, since f is continuous, we know that for all epsilon, there exists delta such that, right, if x minus x prime is smaller than delta, then this must imply that f of x minus f of x prime is smaller than epsilon, right? But now all we have to do is set epsilon to lambda, and if we set epsilon to lambda, then what do we get? We get that, right, there must exist some delta such that, right, if x, so if x prime, or let me write this in another way, right? If x prime is inside the ball, right, is at distance at most delta, so if inside the ball x delta, then, right, then f of x prime is at distance at most epsilon from f of x, so it's inside the ball of f of x, right? And I picked epsilon to be delta, delta, right? So what does this mean? So, so this means in particular that x prime, right, is in the inverse image of this ball, but this ball is inside of U, so it's inside the inverse image of U. And so in particular, the whole ball is inside the inverse image of U, and so it's open. Okay, okay, done this part, right? I just showed that there is a ball around X, right? This ball that needs to be inside f minus 1u. Okay, so then let's do the other side. Right, but these arguments are sort of all very similar, right? And if you haven't seen arguments of this style, just try to draw a picture for like a familiar function and try to see what's happening with these balls and these epsilons and deltas, and you'll see it's not so, right? It's really not so complicated. Right, it's just when we want to do things in sort of full generality, right, it's much nicer to just have these notions of, open and closed and so on. But right, these proofs are all motivated by, either a lot of practice or just drawing a picture and trying to see what goes on. And then, right, and oftentimes you draw a picture for, say, the reals or something like this, and then you try to see what goes on, and you try to understand what is it that still goes on, even if, right, even if you are not over the reals, but over some other metric space or some other topological space or something like this. Okay, so now let's do the other. Okay, maybe I'll do it here. I don't think I need any more space. Okay, the other proof, so this side, right? So if f minus 1u is open for all open u, then f is continuous in the sense of epsilon delta, right? In the sense that we're used to. Okay, this is, I mean, you in some classes you might define continuity exactly this way, and then this sort of feels like a silly statement. Okay, in the sense of epsilon delta. Okay, so let's take x in the region, right? And now let's take y equals f minus 1x. Oh, not minus 1, f of x, sorry. Right, so f sends, f sends x to y. Right, so f of x equals y. Oh, that's already what I have there. Let me erase this better. This is like all getting. That's better. Okay. Okay, so x is in, same thing, sorry. Yeah, x is in y is equal to f of x. Okay, and now let's see, for all epsilon bigger than 0, right, I want to say that if, right, there exists a delta that if x and x prime are delta closed, then fx and fx prime will also be epsilon closed. But right, this is easy now, because for all epsilon bigger than 0, right, take the ball y, or f of x, epsilon, right? Take this as the open ball. Okay, I'll use the notation the ball to mean the open ball, right, is open. And so, right? And so f minus 1 of this ball is also open. But because this is open, right, what does this mean? This means that there must exist, right? Oh, okay, and of course, right, an important point, right? Of course, x is inside this pre-image, right? Because f of x is y. Right, so x is inside the pre-image, and the pre-image is open, and right, there exists delta such that ball x delta, right? Okay, this part is not quite as well erased. Exists delta such that the ball around x and delta is inside that pre-image, right? Because the pre-image is open, so for any point there is a ball there, and so, right, if x prime minus x is smaller than delta, which means x prime is in the ball, we must have that f of x prime is inside this other ball, which is exactly the notion of continuity from epsilon and deltas, right? If for every epsilon, if the points are sufficiently close in the domain, then the image is also close, right? F of x prime minus f of x is smaller or equal than epsilon. Okay, so done. Okay, so let's go into to see what else we can show. Okay, let's make use of this theorem right away. Okay, another theorem. Okay, this again, you might recall if you've taken some point set topology, you might recall all of this, but it's good to recall some of that because we're going to use it. Right? If S is compact and F is continuous, then f of s is compact. Okay, so if we have a continuous function, the image of a compact set is also compact. Okay, this is pretty easy. Right? And here you can see how nice the notion of the notion of compactness that we use. This if for every open covering there is a finite subcovering. Because if it was this notion, say over the complex numbers of closed and bounded, it would not be so trivial to see how to prove this. But with the power, with the power of abstraction, to going into just using the notions of open sets and these notions of compactness, now proving this becomes essentially completely trivial, right? So here's how you do it. So just take, it's sort of clear. There's not much you have. So all you have to do is to take an open covering, right? So take a covering of Fs. So take, say, Ck. Okay, maybe I shouldn't use K. C alpha, say, because, right, there's just some covering for alpha in some set. Let's say an open covering. And open covering of Fs. Okay, so let's say this is an open covering. Okay, so first of all, F minus 1 of C alpha is open. Right? So it's the definition of continuous, or you know, the theorem we just proved. Right? So F minus 1 of C alpha is open. Okay. Also, you know, F minus 1 of C alpha is an open covering of S. Right? There are a bunch of open sets, and every single point in S needs to be in the pre-image of something. Right? Because just take a point X that's in S, right? F of X needs to be in one of these sets because it's an open covering of Fs, and so just take of that one. Okay. Okay, so this means it has a finite subcovering, right? So it has a finite subcovering. Okay, so let's take that. Let's take it, say, right? Let's take it by some other set, maybe, right? So I have gamma, let's say, right? So I take some set T, a subset of this gamma, right? So that now F minus 1, C, let me use another letter to, or a K so that it's clear that it's sort of numbers, right? Because now it's finite, right? Finite subcovering. Okay, so now what do we do? Well, okay, now we move this finite subcovering to F of S, right? Now we take F of F minus 1 of CK. Right? And now this is a finite covering of Fs. Okay, but in particular, you know, I need to show that this, right? So this covers all of S. I need to show, right, that this covers of all of Fs, but also that it's a subcovering of the other one, right? But it's not so hard to see that this is true. Right? And so, right, because if a point, if I had a point whose, right, I take the pre-image of a set. If I take the image again, I need to go back in the set, right? And so now is a finite subcovering of, right, the original covering. Right, and so F of S is compact. Okay. Okay, so just to, for you to think about, take a few seconds to think about. Would this be true that if I said the other way around, that if F of S is compact, then would this mean that S is compact? And if not, then where is the catch? Right, so could I move, you know, like, would the following theorem be true? If F is continuous and F of S is compact, then S must be compact. And if not, then where's the catch? Right, so someone on the chat said that, right, it's not. Take, for example, the sign, right? The image, the sign can take all of R, which is not compact, and just give something that goes from -1 to 1, which is compact. It's the closed interval, right? And what goes wrong is if I have, if instead of f minus 1, I had f minus 1f, this would not necessarily be true, right? Right, if instead of if I had f minus 1 of f of ck, this would not be the same thing as ck. Right, and take something like the sine, for example, and you can very easily see examples of that. Okay, so let's see if we can get some. Let's see if we can get some nice conclusions of this. Right, so let's say that we take f. Yeah, let's say theorem. Let's say f from. Yeah, okay, let's define f again in a region. I mean, it's not so important. But what I want is that f goes to the reals. Right? F is continuous. Right? If S, say, inside the place where it's defined, is compact, then F attains maximum, or attains, I shouldn't say attains, because it has a maximum and a minimum. Then F, let's say, restricted in S, has let me use this notation. Well, let me use this notation. F restricted in S has a maximum and a minimum in S. Okay? It might, of course, not be the maximum or the minimum of the function elsewhere, right? The function might be lower or higher anywhere else, but I now don't know which notation Alfred's uses, but let me say this for F restricted in S, right? But we'll have a max and a minimum in S, right? And how do you prove something like this? Well, F of S is compact, right? And compact sets in R, they're basically, right, they're closed and bounded, and they always have a maximum and a minimum, right? It's compact and compact, okay? We didn't show this, but you can easily show it by just saying that, right, if I have, just imagine there was no maximum and start taking bigger and bigger, a sequence of points that are increasing in a compact set in R, and because there needs to be a subsequence that converges, it needs to converge to the maximum, right? I mean, it's a good exercise to do. It's compact and compact sets in R have max and min. Okay. Okay, let me see if I. Okay, I mean, another theorem, I won't prove this one, but the proof is exactly the same kind of thing, right? That a continuous function takes connected sets to connected sets. Okay, so if you have a connected set in the domain, right, then f of that, if f is continuous, needs to be connected as well. Okay. Okay, so question. Is the same true for sort of the inverse, right? If, say, a set, let's say a set X is connected, F continuous is F minus 1 of X connected. Okay, sorry for the blackboard for being so on the okay, I'll do it here because it's okay. So question is not the theorem. So X, say X connected, F continuous is F minus 1 of X connected. This is the question I wrote down here. Okay? No. right? Someone already said it's not, right? But continuous functions take connected sets into connected sets, but the preimage of a connected set might not be connected. Again, just take sign, right? Look at the preimage of the positive real line of sign, for example, over the reals or something like this. Okay, but now I won't prove this because it's sort of very similar to all the other proofs. But of course, if you know a set is connected, when you want to prove that the set in the image is connected, just take two open sets. They don't intersect each other, and an empty in the union gives the set. Look at what their preimages is. Because it's continuous, they also have to be open. And so that can't quite happen because the first one is connected, and so you get the contradiction. Basically, I just proved it in a few sentences. Okay, but it's these kinds of arguments sort of over and over again. They're very very nice and very useful. A very very useful level of abstraction to prove a lot of things. And I would even go as far as arguing that there's sort of two reasons for level of abstraction, right? One is that as you abstract, you only have to do something once, and you do it already for many, many settings, right? It's definitely very useful, right? There's also the drawback sometimes that examples can sort of be easier to understand at the level of abstraction, at certain very abstract things. However, in these things in topology, I would even argue that arguments become simpler as you abstract. Right? It's not just that you do this once and it's good for the reals, the complex, and any sort of topological space. Actually, the arguments get a lot simpler, and they become a bit, once you get used to it, they become easier to see. Okay, so let's go on to see if I can finish all this stuff to start with integration next week, so that we can prove all the cool results about analytic functions. We need quite a bit of setup before we do that. Okay, so another important definition is the notion of uniform continuity. Okay, so let's do that. So, okay, so, we had convergence, uniform convergence. There's almost for every definition in mathematics, I mean, that's not quite true, but every sort of epsilon delta definition in math, there's the notion of whether it's satisfied uniformly or not, right? Uniformly basically means that, right, uniformly is sort of in continuity would be for every epsilon, like for every point and for every epsilon there exists a delta, right? Uniformity means when the delta doesn't depend on the other parameters, right? That's what one means usually by uniformity. Of course, now, you can ask, okay, so what parameter should it not depend on? If it didn't depend on on epsilon, that would be kind of strange, right? If I said for every epsilon and every x, there's a delta that now doesn't depend on epsilon, right? And if you think about it, the functions basically need to be constant, right? But what we can ask for is that the delta does not depend on x, right? That sort of the epsilon delta game you have to play can be exactly the same for every x. Okay. So definition. Okay, uniform continuity. Right, so for every epsilon, there exists a delta, okay, of course bigger than zero, such that for all x and x prime at distance. Right, I'm using here the distance, but over the complex numbers, of course, you would take this. But it's just because you might have spaces in which you can define a distance on which you cannot define what it means to subtract something by something else, right? And so, okay, and so such that this delta, sorry, implies such that we have, right, that f of x prime, distance between these things is smaller than epsilon. Okay, so this is the notion of right. This is the notion of uniform continuity. Okay, and now easily you can already prove a theorem. Right. So when can something be not uniformly continuous? Right. If sort of the epsilon delta you need, the delta starts getting smaller and smaller as x approaches some kind of point. Right. That's usually typically what can happen. Right. But now, if you have, if you take like the square, f of x equal x squared on all the real line or something, then, right, it's not so easy to see that you cannot, right, it's not uniformly continuous. It's definitely worth doing the calculation, right? But as we already saw, right, things over compact, over compact spaces, they sort of always tend to have a max and a minimum. And so we would expect that if something is continuous over a compact space, then it actually needs to be uniformly continuous. Right, on compact spaces. Sets continuous functions are uniformly continuous. Okay. Okay, and so I don't think I have time to prove this before the end of this time, but the proof is very much okay. So I'll sort of decide if I do it in the next one. I'll just skip it, but the proof is very similar to all these other proofs, right? It's a very good example of how to use the definition of compact set in terms of open coverings, right? So for every point in the compact set, say every point x in S, you build a ball on which you have on which you have continuity with a certain relation of epsilon and delta, right? And like you build a ball for this. Now you build a ball for each one of these of the sets in S, right? And now this will be an open covering, right? Many times these types of arguments, the way they go is for every point you define a ball around it that satisfies a certain property you want, right? Like satisfies this continuity with a certain epsilon delta, right? So you fix epsilon and with a certain delta. Right? And then because it's compact, this open covering will have a finite subcovering, right? So this means that actually you can cover the whole space with just a finite number of these, right? But a finite number of these means that it makes sense to talk about the minimum of these deltas, right? Because now you only have a finite, so on the finite subcovering, you can talk about a minimum of such deltas. And this and then you have to work a little hard because, right, not very hard, but you have to do something else because you have to also understand how, even though you have, right, the balls covering everything, you might be interested in an x and an x prime that may not be in the same ball, and you might be interested in relating them. But it already gives you the hint that you can consider such a thing as a minimum delta. And basically, if you do it with like delta over 2, all these other issues, they get fixed up, right? And this is how you prove this. And so I'll see during the break, I'll see. I really want to get to integration next week, so I might skip this, we'll decide.